Okay, so hello everybody, and welcome to this last colloquium of the Institute of Cosmos Sciences of the year. So today we have the pleasure to have here Professor Alfredo Poves from the Autonomous University of Madrid, who is actually just in a glimpse, a world expert in nuclear structure and in particular in shell model calculations. And just to give you, I mean, he has many honors and has participated in many also bureaucratic and important things. So for instance, he was vice rector of the Autonomous University of Madrid, chairman of the Department of Theoretical Physics, chairman of the Institute of Theoretical Physics, or Instituto de Física Teórica in Madrid, and also he has been member and chairman of the board of directors of the ECT-STAR, the European Center for Theoretical Physics in Trento. He has participated in the program advisory committee, for instance, of ISOLDE in CERN, and in other experiments, like in the program advisory committee of FAIR. And finally, he has been member of the editorial board of Physical Review C and Nuclear Physics A. So today he will be discussing essentially about the shape coexistence in nuclei. So I hope we all learn a lot of nuclear physics today. So thank you very much.
Thank you very much, Bruno, for the introduction. You have many things because you are also many time behind you. This is one of the things that makes that you have been in many committees and things like that. Thank you very much to the organizers for the invitation. It is a pleasure to be here again. I have been here already many times in other circumstances, but this is always a pleasure. I will be discussing shape coexistence in nuclei, and I will have a mixture of things, and some of them will be old wines in new casks, let's say, things that are classical, and I want to give a little twist to at the level of the nuclear physics that you teach incorrectly to the students, I will say. Okay, this is the outline of the talk. I will give some motivation in relation with other fields for my colleagues here not to be completely abandoned from the beginning. On nuclear physics themes. Then I will try to convince you first that the problem is very complicated, but if you look at it from another corner, it may be very simple. And then I don't want to change the combination of colors to improve the presentation. They have asked me something. Then I will discuss some of the main elements of nuclear physics, which makes this system fascinating and different to the other many body systems that you know. And this is about the quadrupole interaction and the shapes. And let me go here. This thing will end with shaking the pillars of our knowledge of nuclear physics, of elementary nuclear physics, and then I will be visiting the regions that are experimentally more exciting now, which are the region of the chart of nuclei, which are far from the stability. And now it comes a chart of nuclei where you have the number of protons and the number of neutrons here. Each pixel is on isotopes. The black dots are the stable nuclei. The stable nuclei go up to very few, 300, in different colors. Colors, I say color, and it reacts immediately with that. No. Or I don't say color again. It's another possibility. Okay, so I cannot. This color codes means that your beta plus emitter, beta minus emitters, all these pixels are nuclei which are unstable, made in the labs. Yellow is alpha emitters, green is spontaneous fission, and all these beauties of radioactivity. But the gray part is those that we know should exist, but in some can exist, but have not been made, but can be made in astrophysical scenarios. And the importance is that if you don't know the behavior of those, you cannot explain how the nucleosynthesis, for instance, evolves. So you need a lot of effort in modeling and having data. One important thing is that here you have what is called the proton drip line is when you cannot add a proton more. And this is important to know because these are the very limits of existence of nuclei. In this side, you will have the drip line for neutrons that you know is very, very badly known for the moment. Different models give different results, etc. And it is very far from the nuclei we know. And the interesting thing is that some astrophysical processes, for instance, the rapid neutron capture process that produces most of the heavy nuclei, proceed in this unknown territory. So really, we don't have in the lab any information about that. And there is a huge effort in moving into this territory experimentally and theoretically. And finally, this is the limit of heavy nuclei. In this region here is where it is supposed we can find an island of stability of super heavy nuclei that the community, we are approaching slowly, and I had a transparency, but I discovered that this is much better, and the outcome of these searches is the completion of the period. Oh, whoa. I have shown all my secrets. The completion of this part of the periodic table with this super heavy nuclei like organeson that has C equal 118. So this is an outcome of the nuclear physics work, experimental work, trying to produce the heavier and heavier nuclei. So these are the three limits: proton drip line, neutron drip line, or neutron-rich nuclei, super heavies. I will concentrate, I forget about the super heavies, a little touch on the proton drip line. I will be more in the neutron-rich region, which is where new results have happened. And this is again the Segre chart with this unexplored territory, and these are the paths of the art processes that we need to model theoretically, because experimentally it is not possible. Okay, you know that one of the aims of nuclear astrophysics is to know how the chemical elements have been produced in the universe, and this is related also to nuclear physics, where these elements were made and how. And this is the plot of the abundance of the elements in the universe, and this is one thing one would like to reproduce theoretically. And we know that several paths produce these elements and several scenarios. You know that light nuclei are produced after the Big Bang, but very few, again, indeed. Then you know all the processes that occur of fusion that occur in the stars, but then you find the wall of iron 58, 60, where you are not exothermic again. So all the others need to be cooked in other scenarios. In particular, for the air process to go on, you need a lot of neutrons. And for many, many years, the favorite site for the air process were the supernova explosions. But there was always a tension with reality. And somehow, and very recently, with all this multi-messenger stuff, it turns out that the favorite candidate now for the R process is our neutron star mergers, which were detected after the gravitational signal, in particular this famous one in August 17, no? August 17. And now this is the favorite candidate, and I cannot resist to present this transparency that I borrow from someone that you probably know, because he spent 3 years here in Barcelona at the Instituto de Ciencias del Espacio, which is Gabriel Martínez Pinedo. These guys with collaborators in 2010 predicted that which would be the light curve in this process of neutron-star mergers that correspond to really going up in the R process and then decay to stability. This produced a lot of decays that they model, and this was 7 years before, and this was the curve that they presented in 2010, and these are the experimental points of this observation of the kilonova, which is the name they have coined for this phenomena, this kilonova. So I'm very proud of this result, not the less because Gabriel was my PhD student. And obviously he's better than I, and this is the goal of someone. Okay, let's then move from astrophysics to fundamental physics, other domain where to know well the nuclear physics is important, and I have singled out the process which is the neutrino-less double beta decay. This process, if you measure this decay, neutrino-less double beta decay, this will fix that neutrinos are Majorana particles. And this is beyond the standard model. This is something which is important. And there is a huge international program, underground physics, you know, NEXT in Spain, or DUNE in the States, or Gran Sasso. There are many experiments searching for these rare processes. But from a point of view, which is important, is the almost, how do you say, the random possibility of having this process, because this process can be detected only when the single beta decay is completely suppressed, because if not, you don't see anything. This is a second order, obviously. And this only happens in nuclei because you have an interaction which is the pairing interaction. The pairing interaction favors pairs of identical particles against not being pairs. And this means that if you represent the masses of corresponding to the isotopes with these isobars, with this mass, A equals 76, you see here, if you see that you have two parabolas, one parabola are the even proton, even neutron nuclei, and the other is odd. And they are split apart, because in the odd, you can make a pair less, no? And this you lose energy, and everybody is displaced. That is first lecture in the course of nuclear physics. No? And so you see that this poor germanium-76, he cannot decay by single beta decay. There's no way. So the only possibility is go to the selenium, but this is a second order process. And you have two possibilities. Doing the second order process with emitting two neutrinos, which is trivial, it's second order in the weak interaction. The process is very rare, but has been measured, and we know the lifetime, is well understood. But what is interesting for beyond standard model physics is if you have the possibility of getting the neutrino-less stuff. And this is more or less the same. In this case of the two neutrinos, these are the lifetimes. 10 to the 22 years is already athletic to measure that. But now the expected lifetimes of the neutrino-less go beyond 10 to the 25, not to be too cruel with experimental friends, because I will say this probably 10 to 26, and this is a catastrophe for them. Okay, this is a cartoon that was prepared by Tomás. Rodriguez are completely unable to do these funny things, but this is the diagram where the neutrino becomes its antiparticle, it annihilates and then disappears, and in the final state you have the final nuclei. You have changed two neutrons into protons, you emit two electrons. The important thing here is that the lifetime of the process is related to the effective mass of the neutrino. If you measure it, you know that it is Majorana. But the lifetime is related to phase space plus the effective mass of the neutrino. That you want to know, to say, is to know how heavy is the neutrino. But in order to go from here to here, which is very important for beyond standard model physics, you need to know this matrix element, which involves the wave function of the initial and the final nuclei. So if you don't have that, you really spoil your experimental information, if you have this experimental information in some time. Okay, so now let's move more into theory, into nuclear. Obviously, if you want to explain all these phenomena, many others, to know where are the drip lines, etc., you need to solve the many-body problem. And the many-body problem in nuclear physics is especially difficult because the interaction, which is not QCD, this is a kind of derived, is an effective interaction which comes from gluons and quarks, and it has all the complications that you don't like to have in one interaction, including the need of three-body forces, three-body interaction, explicit, and also that you have many nucleons, but not an infinite number of nucleons. So every nucleus is different to the neighbor. So it's really a fascinating problem, but complex. In order to solve this problem, you have two lines of work. One is to incorporate the correlations. One is mean field, let's say. Sophisticated evolutions of Hartree-Fock, where you break the symmetries and you incorporate the correlation by breaking the symmetries, and then you restore the symmetries, and well, this is all the line of the mean field approaches in the intrinsic frame initially, and then what we have been doing is to remain in the laboratory frame, because it's there where the experimenters are in the lab. They are not intrinsic at all. And then there has been advances in this line, solving the many-body problem, projecting into valence space that contain the adequate degrees of freedom of your problem, and going from one effective theory to another effective theory. At the end, you can contact, as you will see, with experiments. A long and windy road of the effective theories. Okay, this looks very complicated, but I will offer you a glimpse of a view of the problem, which is, at least for me, very physical, and requires for you to change of your space, quantum space, from the ordinary space to the space of the states, which are solutions of let's say, a spherical Hartree-Fock approach to the problem. If you want to complicate, think in the states of the independent particle model, Meyer and Jensen 49, that you teach or you learn at the graduate school. Then you have states. This gives you a basis, which is in principle a basis as good as any other, and then you can recast your problem in this basis and think in configurations in this basis. If you write your Hamiltonian in this basis, there is, you analyze it properly, simplicity comes out. I cannot enter into the detail. Believe me that you can take your Hamiltonian in this basis and separate in two parts. One part which is HM monopole, nothing to do with the, except I will tell you that monopoles in this context means operators, terms of the Hamiltonian that only contain operators that are number of particles in states. So they do nothing, just count. Just count things. And the rest of the Hamiltonian is the multiple, which are the correlators. No? The multiple will take this inert configuration, mix it, and produce things. This is the separation and the physics, which is simple in a sense. This monopole can be written like this. And you can put any polynomial in the number of operators. If you have three body, you can add a three-body number operator, and it is trivial to solve. It's not a many-body problem either. It's just trivial. Each configuration gets an energy, period. Contained in this monopole are the pillars of our shell model description, Meyer and Jensen again, which are the magic numbers, which are the justification of using, in a sense, a shell model for the nucleus. But this is encoded completely in the monopole part. Which are the contents of the correlator? Which are the most important correlators in nuclear physics, in the nuclear interaction? They are two. One is pairing, and one is quadrupole-quadrupole. And then I come to this lambda equal 1 that I have put here as a control parameter. Imagine that nature has decided in this that lambda is equal to 1. But now I will play to the master of nature, and I will put lambda equal to 0. Lambda equal to 0 is very close to atomic physics, where a good Hartree-Fock or Dirac Hartree-Fock is already an extremely good approximation. If I take lambda equal, let's say, to 100, then the solution is probably also trivial, because the solution will be that all the nuclei are superfluid needles. They will deform as much as the Pauli principle permits, and they will be superfluid. If the lambda you take, if you put a lambda on this term and put 0 in the quadrupole, then you have a superfluid period. So there are three limits, three natural limits. One is the independent particle model glorified. Another one is the superfluid, and another one is maximal deformation. In all three limits, you have easy solution of the many-body problems. In reality, you have to make a cocktail of that, and this is the fun. Okay? Okay. So let's come to the magic numbers that are associated to large energy difference, as in atomic physics, between configuration, and that were the pillars of the shell model. These are there, these nuclei are there, are few. You know that you have the magic number that are 6 or 7 for protons and neutrons, so you don't have so many double magic nuclei. Most of the nuclei are deformed. This is telling you already that the correlator, the quadrupole correlator, is dominant. So I think that we don't insist enough in the nucleus as a highly correlated fermionic system, where in most of the cases, the spherical mean field approximation is just a reference and not a physical description. The mean field gives you a basis, but the physics is not contained in this basis. It's contained in the mixing of thillions of Slater determinants, as you will see. And let me go to a textbook example of a nucleus that Javier studied in his PhD thesis. This is calcium-40. This is a double magic nuclei. And indeed, the ground state is a 0 plus, which will be a double magic. Everybody goes in this direction. But if you think that you have a gap, which experimentally in calcium-40 is 7 MeV, and you think in terms of particle holes across the gap, you will expect a hierarchy of excitations going from 7 MeV, 14, 21, many particle, many holes. This will be what you would expect naively in an atomic physics context. But what is nature telling you? That you are wrong. The first excited state of calcium-40 double magic is a variant of calcium-40 which has decided to be deformed. This is nuclear allotropy. It's coincident of different shapes in a very small energy window. And the funny thing is that this state, when you look at it closely, is of 4-particle, 4-hole natures. So you will expect it at 24 MeV of excitation energy, naively at the spherical mean field level. And it is, at the end of the day, nature put it at 3 MeV. This means that the correlators had given this state 25 MeV of correlation energy. Imagine that I tune my lambda in the other transparency instead to nature 1 to 1.1. Then the ground state of calcium-40 will be deformed. Magic numbers will have, these have never been found. Gepper-Meyer and Jensen would have the Nobel Prize, and we were studying nuclear physics in another completely different way of approaching it. This is shaking the pillars. And this is not exotic, it's not far from stability. This is just old and well-known calcium-40, double magic. Okay, why are the quadrupole correlations so efficient in nuclear physics? It has to do, you can understand that if you think that you can simulate the mean field by an oscillator, and the oscillator, the harmonic oscillator, has an extra symmetry, which is SU3, and the 3 of SU3 are the 3 directions of space. But the group structure is the same, and everything which has 3 things is SU3. The generator of this SU3 are the angular momentum and the quadrupole operators. Therefore, if your interaction has an interaction which is quadrupole-quadrupole, and you think in the representations of this SU3, the representation that corresponds to the large Casimir operator will be favored. And this match between the structure of the mean field of the states and the interaction makes the terrain very, very prone to produce deformed nuclei as it happens, okay? So there is a lot of variants, but one that I love is the case where you have protons and neutrons in a major oscillator shell, an attractive quadrupole-quadrupole interaction, because this is analytically solvable, and the solution is that you get the maximum deformation, which is allowed. The lowest energy corresponds to the maximum deformation. This is Elliott's model, and this is one of, in my opinion, of the cornerstones of nuclear physics. There are other possibilities. There are many other variants of SU3 I will not discuss. And I will go to again to the title of the talk, if you're not too tired, is shapes. When you speak of deformation, you are using a semi-classical language. You are somehow thinking of a drop that can be spherical or can be deformed in many. And then, as I say that, the surface of a drop can be expressed in the basis of the spherical harmonics. The coefficients of this development are the shape parameters. If you remain to the lowest order, which is the quadrupole, Y2, you have only two parameters, which are the famous parameters beta and gamma, which describe the shapes, the ellipsoidal shapes. Beta is the global amount of deformation, and gamma will tell you if you have a rugby ball or a lentil or something intermediate without axial symmetry. But you have these two parameters. Don't forget that these are things that are geometrical in nature. It's just a drop, things like that. So in what happens in quantum physics, we have assumed, we use, and I say my mea culpa, my particular mea culpa, we live very easily with this idea that the intrinsic frame is reality, and we speak fluently about shapes, etc. I will at the end tell you that maybe we are overusing this semi-classical description. And then, as promised, I will go a bit into the physics. This is a part of the table of the Segre chart below tin 100, where you have the n equals c line. This is stable. This is not stable. The stable is rather these guys always run out of batteries. This is a theorem. Whatever you do, it's I running out of pressure. Okay, so this n equals c zirconium is unstable. The stable is more or less here. And in the tin isotopes, the stable one is 120 more or less. You need 20 more neutrons to go there. So this region is already a region of proton rich, and the other side you have neutron rich. For instance, you have nickel 60, which is stable probably, but you have made in the lab nickel 78. I will present you something about nickel 78. So you go very, very far in neutrons, and you enter in this region, which is important for the R process, because this nuclei is crucial for the path of the R process, and then it has a strong influence in the prediction for the abundance of the chemical elements. And you have many others. All these regions here have been explored recently in the last, let's say, 10, 20 years. I will have select some topics, just read it, physics issues at n equals c approaching the proton drip line. There is another contact with another line of contact with the fundamental physics is through the super allowed Fermi decays, where you can get information about some terms of the which is the one that the quark matrix, which is Kavivo, Kobayashi, Mascava, whatever matrix with this. There is also a connection with fundamental physics. There are issues of isospin emission, proton emission, proton-neutron pairing, and also the always coming question of whether magic nuclei survive when you move very far from the stability line. I will only show you one. No, I will not show you anything unless. Ahora ha pasado algo. Ahora es que no puedo hacerlo. Esta vez no puedo. Can you go to the following? You? Can you go to the next slide? Okay, thanks. Only one example, one of the exotic nuclei, proton-rich, thank you, proton-rich that have been produced in the lab is, the other side is a very exotic tin isotope, is 100 tin, is double magic, it's 50 and 50, and it has been measured in the decay, the beta decay has been also measured, and it produces a matrix element that is huge compared with all the others. So this point here is the log ft of this decay is the smallest ever found. That's like an hyper allowed gamma-Teller decay. This was just for giving you an example. Okay. At the neutron-rich side, you have many other physics issues. I will not talk about halo nuclei, but you have new magic numbers, safe coexistence, etc. And this will be the topic that I will go through if this thing decided. Yeah. The key point now is that if you go far from stability, you are in circumstances where you have semi-magic nuclei. You have a double magic nuclei, and you remove or put protons on or neutron protons on top of that, and you will expect that this nuclei, as you have a magic closure, will be not prone to become dominated by the quadrupole correlation. But in fact, it happens quite often. And when we have this inversion of configurations, we speak of islands of inversion. I will show you the mechanism, which is well, it's quite not fully universal, but it repeats several times. And I have prepared a cartoon here. Concentrate, for instance, in chromium 68. In chromium 6, or rather in magnesium 32 here. These are the orbits, and this will be the Fermi level that you expect to be the ground state, with neutrons closing the n equal 20 magic numbers. That is what you expect. This is normality. But you have the possibility of promoting neutrons through the Fermi level. And we have learned in the case of calcium-40 that this open cell configuration can gain a lot of energy by the quadrupole interaction. And indeed, it is what happened, and in several cases, and these are the Island of Inversion, these particle hole configurations become more bound than the normal filling configuration, and then you have a shape, a quantum phase transition from nuclei that are, let's say, closed shell to nuclei that become deformed. And the mechanism is very general in many regions of the periodic table where the quadrupole interaction is comfortable. Okay, so this is another cartoon of which are these regions of nuclear, very neutron-rich nuclei, where this phenomena of inversion occurs. And there is 1, 2, 3, 4, 5 islands of inversion corresponding to n equal 8, 20, 28, 40, and 50. This is what is known for the moment, because in this medium mass nuclei is where you can really go very far from stability in the experiments now. And also where you can do proper calculation, which is another important issue. So you have here some protagonists of this: magnesium 32, chromium 64, chromium 74. And I will show you some results of our calculation very rapidly without technical details. I will use in 2 cases in where you have a double magic nuclei and then an island, an adjacent island of deformation. And this is very general. I will start with n equal 40, and this is shape coexistent in nickel 68. Nickel 68 is in the ground state double magic, if you want, and I have put here a spherical, my fault. But if you see here, you have here another 0 plus, first excited state, that correspond to another shape of the nucleus. Now it's like a lentil, it's oblate. But a bit higher, you know, the energy is very low. You have another structure, coexistent, which is prolate. So it's a triple. You have 3 structures in a very narrow energy domain. By the way, we are able these days with the largest scale shell model calculation to give a very quantitative prediction or description. The funny thing, and this is very general, is that if you find this shape coexistence in a double magic nuclei, and then you remove protons, which means open up the proton shell, these excited configurations go through the normal configuration, you produce the inversion, and you enter in the island of inversion. So the shape coexistence in double magic nuclei is the portal to the islands of inversion. And let me show you that in these results. These are the 2 plus energies. 2 plus energies of closed shells are high, and in the form case and very low, and the transition probability go the other way round. So you start with nickel 68 with the 2 plus, and just removing 2 protons, the 2 plus drops, and nickel, iron 66 become the form. And so is for chromium and titanium. And consistently, when you move in the transition probabilities, you make a huge jump of a factor of 10 or something like that in the transition probability. In iron, in chromium, in titanium is not measured yet. The 2 plus energy of the titanium have been measured 1 year ago. Don't take that as an exaggeration, but this is the point, and this was our prediction 10 years ago, more or less. Not every day you get that, at least me. Okay, same thing, if you go even more neutron rich to n equal 50, you have the same phenomena, but now you are becoming seriously exotic, and this is a calculation, because it was previous, of nickel 78, where the ground state again is the same. It's double magic, but you have a deformed structure at low energy. As we learned that, it's obvious that if you move to iron and chromium, this structure will become the ground state, and you will have another island of deformation. And this is what happens in the calculation. First, let's say this is the comparison with with experiment just a few months ago, where these two pluses compatible with our calculation have been measured. So there is this coexistence is there, experimentally, which is the important thing. And our prediction of the fifth island of inversion will tell you that if you go to chromium 74, it's just like taking this excited structure. It's very spectacular, because if you take that and you move it to chromium, the overlap is perfect. It's just that. It's very simple in nature. Okay. This is perfectly, if it was, it's slow or no? You are doing that, do it rapidly. Okay. That's the end for my walk in the neutron-rich side with all these things. And let me just for fun to tell you something about what happens with the concept of shape if you do it properly. And this is that. There is only one way to move between to establish the conversation or the meaning of the laboratory frame parameters, the intrinsic frame parameters going to the laboratory frame is through quadrupole invariants, which are just rank 0 tensors of different order. And these are the quadrupole invariants that you can construct Qn. It turns out that if you construct the Q square and the Q cube, you can relate these two invariants precisely with the beta and gamma parameters that describe the shape in the intrinsic frame with these classical formulas. You have beta is just the square root of this invariant, and the cosinus of 3 gamma is related to the third order invariant. So we are very happy. We can get these two numbers which are semi-classical in an invariant way. Well, not so happy, because you can compute this value, but if you dare to do it, you can compute the fluctuations of this gamma with the higher order invariants. You need to go up to 6 order invariants to get the variance of these quantities. And when you do these things, which you do, these are the formulas, don't worry about that. The important is that you have the value of these shape parameters and the variance. Then you get to these funny conclusions. Do the intrinsic shape parameters survive in the laboratory frame? Well. Beta, yes, but with a large fluctuation. Typically, sigma q squared is equal to 0.5 q squared, which is not very brilliant if the width is 1/2 of the mean value. This is a large fluctuation. And definitely gamma goes bananas. Gamma is completely washed out when you go to the laboratory frame. It doesn't survive. No? Only in some limits, which can be when quadrupole is so dominant that you can think that this is SU3. In this case, the fluctuations go to very small or go to 0. And probably this is the reason why in very heavy nuclei, where you are really in the extreme quadrupole limit, these parameters, in even gamma, may have a sense. So I'm not completely breaking everything, only just making some warnings. And to finish, or almost finish, in a provocative mood, the conclusion of this study is that double magic nuclei, in all the text is said, books, is said they are spherical. Well, no. Double magic nuclei are not spherical because they have no shape. If they are double magic, you cannot define a shape. To define a shape, you need to define an intrinsic reference frame, and you can't. So, at the end of the day, you don't have a spherical nuclei because you don't have the right to speak of shape when you are in these places where you wanted to name spherical. So, we are over-naming the shapes, in a sense. If you take the classical double magic and you compute with the invariants the beta parameters are and the gamma parameters, what you don't find is nothing. In principle, you need to have beta equals 0. No, you have whatever you want with a huge fluctuation, which is physically very sensible. We were abusing of the language. So it's a bit discomforting, but I will finish with the case of this nickel 68 because I have made drawings with this 1 sigma fluctuation which are very telling. What is that about shape coexistence? Next one, please. This is the beta gamma plane. This is gamma and this is beta, and this is in the ground state, which is double magic. The point in beta and gamma is not here, is here. But look to the shadow area of the fluctuations. It means nothing. Huh? Something which has a sigma of beta, which is equal to beta typically, and you can explore all the gamma values at 1 sigma, and even more. So in these cases, you can use the proposition 7 of the Tractatus Logicus Philosophicus de Wittgenstein, which in vulgar Latin I can translate, if you have nothing to say, you better shut up. He explained it more in a better English that I have somewhere. Whereof one has nothing to say, thereof one must be silent. Okay, previous one. In the case of the oblate, you see again the same phenomena. Here the deformation is larger, but still, if you are at 1 sigma exploring all these things, can you really speak of a shape? I have my doubts. And next one, in the other direction, in the advancing. Okay, and this is the prolate. Well, here, as you are already at large deformation, this is beta soft, but you can live with that. And you are living in a part of the quadrant, but gamma is so ill-defined that you better forget about these things that have been our bread and butter for many, many years, I would think. With that, I think that just letting to you not to read that and move to the conclusion and read it if you want. I thank you a lot for your patience and attention. Thank you very much.
Okay, thank you very much for this very illustrative and also provocative colloquium. So we have time for questions.
So I'm not an expert on this, so I may say something completely stupid. But so it looks like there are these two parameters, gamma and beta, and you say that when the mass of the nucleus goes to infinity, let's say they become very large, so you get that basically you don't have fluctuations, no? And then you can fix this gamma and beta. So I'm wondering whether there is like an effective field theory approach of this thing, because this looks like in particle physics when you have operators that are suppressed by certain scale, and when we send this scale to infinity, then basically this, I mean, the system can be described as a free system, and then everything is fixed. So maybe there is an effective field theory approach where you can actually take operators in Q suppressed by the mass of the nucleus, and then get the description of shapes you want. I don't know if this is possible. Maybe it's stupid, but...
No, this is also, my answer is I don't know. I have never thought in these terms. You can really imagine some kind of it's a complicated, the moving from the fully quantum system to the semi-classical limit is also a problem. You can do it in many ways. In my view, I had rather thought of associated to the transition to the restoration of the symmetries associated to the quadruple degrees of freedom. Probably this can be put in a language. Almost everything can be put in the language of an effective theory. So why not?
Any more questions?
So, so for you, what would be how to reconcile this effective and efficient framework that you develop? So how would be reconciled with the existence of short-range correlations between the nucleons? Or in other words, what would be the signals here of the short-range correlations that should produce a depletion of the low shells and a large occupation of the very excited shells? There is any signal or anything to comment about that?
Well, we live in this effective, we have a tower of effective theories, one on the top of each other. And in these towers, there are, when you move to the next tower, you get operators that are completely different. So when you put this short-range correlation under the rag, but it comes out producing necessarily effective operators that are very different from the bare operator, and this happens. You can see that experimentally in the spectroscopic factors and in many other observables. This is the price that we have to pay to live in this comfortable basis of a kind of spherical mean field of reference. This is really, and you pay a very big price through this this phenomenology associated to the operators. You're completely right.
Any further questions or comments? I wanted to ask just one thing. When you have this multipolar term that induces correlations, you said in the system, are these correlations independent of the single particle bases you use?
Yes. I mean, you start with in the tower of effective theories, you start with a chiral. Imagine that you start with a chiral perturbation theory, which gives you an interaction. Huh? Mm-hmm. And then you put it in the tower, and you continue having this interaction living in the normal space. So it is completely independent in this sense of the basis. Only at the end of the day, when you define your basis, you need to compute matrix elements of these operators in this particular basis. But the interaction, hopefully, is the one that you trained from your basic description of the nuclear-nuclear interaction. Hopefully, yeah?
Yeah, a little bit in the line of Arturo and Bruno's questions. I wonder, all these no-core shell model calculations, do they have this quadrupole interaction that you are? No.
Yes.
Yes, it is already there also.
Yes, it's
in
there.
this,
There is nothing put by hand. No, all this is the nuclear-nuclear interaction that gives you. It is there. As a matter of fact, let me tell you one thing. With all this ab initio stuff, etc., they can produce interactions, which in principle don't make this renormalization at the same time of the short range. Let's say you can do it in a proper way, more modern than the old G matrices, etc. And at the end of the day, if you analyze with some tools that we have that are very telling, the content of these interactions, this quadrupole, and pairing, etc., is the same. It hasn't changed since Kuo-Brown. It is the important part which changes is precisely the monopole. This is completely different, because this is related to saturation and things like that, which is are the bulk stuff. But these little details of quadrupole it is what it is. It hasn't changed a lot.
Okay. Any further questions?
For instance, these short-range correlations then could show up in the monopole terms, for instance?
Yeah, they show, but you have difficulties nowadays. No, I'm sure they are. They must be there. They must be there. Point is that when you know that when you start doing that, at a given moment in this chiral stuff, it is difficult to disentangle short range and free body and things like that. There is not, Javier knows more, but there is not a trivial way of separating exactly, but it would be interesting to explore that.
Are any further questions or comments? If not, let me first say one thing, is that at 4 p.m. Professor Poves will meet with PhD students from the Institute and postdocs. And with this, let's thank him again for this nice talk, and thank everybody for coming.